So we talked about how unshared pairs, like on this here water, and I'm actually missing an unshared pair, but unshared pairs change the geometry of a molecule, and that's really the heart of Vesper theory, that you have valence shells and electrons that are repelled by one another. You know, that's kind of the key piece. And building all these, do you feel like after building them you have a better idea of how those Lewis structures translate to a three-dimensional universe? Did that help, like comparing the two of them? I think for most people it does. If it didn't, did anybody have any sort of what I'll call cognitive dissonance with, well, wait a minute, but how does, with any of that? Yes? Okay, so here's what I'm hoping you had cognitive dissonance about. So if we think about where those valence electrons actually are, where is that single valence electron in the hydrogen? What's the electron notation, or orbital notation for hydrogen? Electron configuration. Geez Louise, I'll get it yet. 1s1. Yeah? So what about oxygen? It's got 6 electrons, 6 valence. What's the atomic number of oxygen? Atomic number. It's got 1s2, 2s2. You might want a periodic table out. 2p what? 2p4. Okay, well, great. So if we think, I mean, you know, hydrogen's pretty darn easy. You've got a 1s orbital. It can share one electron, and then that little s orbital feels like it's full. Everybody's happy. But oxygen's a little bit more complicated, isn't it? Because, you know, this one's out of the race for bonding. It's lower level. This is not something that has expanded valence. So everything is bonding here. If we do the orbital notation for this, 2px, 2py, 2pz. 1, 2, 1, 2, 3, 4. Okay, well this one actually does work, huh? So, you know, this p orbital kind of sidles up to this s orbital, and this p orbital kind of sidles up to the s orbital on the other hydrogen. And they hook up. They share electrons. Everybody's happy. But let's look at something that doesn't work so neatly. Let's look at carbon. You know, you're all carbon-based life forms. Carbon's awesome. If you take organic chemistry, the first thing you learn to do is count to 4. Because carbon bonds 4 times. Carbon always forms 4 bonds, whether it forms 4 bonds with one thing, or 3 bonds with one thing and 1 with another, or 2 double bonds, or a triple bond and a single bond, whatever. Carbon forms 4 bonds. So what would the orbital notation be for carbon? What's carbon's atomic number? 6. So number 6, so it's got a 1s2, 2s2, 2p2. So remember, this one's totally out. So if we look at these valence electrons, we have 2s, 1, 2, 2px, 2py, 2pz. Whoop, whoop, whoop. 1, 2. So how many bonds does that look like it's going to form? How many orbitals right off the top? So we know carbon forms 4 orbitals, like we know the punchline. But it looks like, you know, let's talk about hydrogen, you know, with its little 1s. You know, this 1s could sidle up to this 2p, and another 1s could sidle up to another 2p. Then could another hydrogen bond. Jeez Louise, Moser. Could another hydrogen bond here? No. So how does this work? We know that carbon forms CH4. It bonds to 4 hydrogens. How does it do this? One of these orbitals is already full. One is totally empty, and you've got these 2 that each have 1 electron. So it's got 2 spots where you can look at it and say, oh yeah, those bond. But I don't see 4 bonds here, do you? And yet, carbon-based life forms, Gesundheit, it forms 4 bonds. So this is where we get into this weird thing. Remember how we said, oh yeah, there are these defined orbitals, and Schrodinger's equations, predict these geometric areas, 3-dimensional space where electrons are likely to be found, and this is set in stone as something that you can't measure its velocity and position at the same time can be, and it's constantly in motion. Well, do you know what a hybrid is? What's a hybrid? What's a hybrid corn plant or a hybrid dog? Mix between 2 things. So hybrid is a fancy term for mutt. If you go to the pound and adopt a hybrid, you can very proudly show off your hybrid dog. It's a mutt. That's okay. They're more robust anyway. Don't get a purebred. So what we have is this thing called orbital hybridization. So we said a hybrid is a mix of 2 things. And turns out orbitals hybridize. So you mix 2 or more atomic orbitals of similar energies, and what you get are new orbitals of equal energies. So we are going to talk about methane. This is the easiest one to talk about. If you go on in chemistry beyond like general chemistry 1, you'll get much, much better at hybridization. We are going to skim the surface here. This is very much surface skimming. So in methane, so where were we? We get this hybridization. We're going to talk about methane because it is a really, really easy one to talk about. So we said we had that little problem with methane where carbon has, well, we'll forget about the 1s even. It's got 2s, 2px, 2py, 2pz, zoop, zoop, zoop. And it looks like that. But that really only allows it to form 2 bonds. So what happens is you throw 1s and 3p orbitals into a pot. And if I had a way, I would do something like this. And then there's a swirl, and then there's a cloud, and there's magic, and there are words, and there's a puff of smoke. And what you get out of that whole mess are four brand new orbitals that are a hybrid of 1s plus 3p's. And they each get 1 electron. So chemists and the kind of like molecular physics people being really, really creative, if you put 1s orbital plus 3p orbitals together, they call it an sp3 orbital because it's 1s plus 3 p's. They're super creative. They're a lot of fun at parties. Really funny jokes. Yes?
Is this for carbon that does that?
Awesome. That's good. You're paying attention. So the question was, well, how can carbon do that? It's only got 2p orbitals. No. It only has 2p orbitals that have stuff in them to start with. It's got all 3 of them, though. And so you throw these four into a giant pot, and what you get out are 4 new orbitals. They are equal energy. So all that stuff we said about, orbitals fill, every orbital of equal energy gets 1 electron before anybody gets 2, all those rules that we learned, they don't go out the window, but they get tweaked. Because now you have 4 orbitals that are equal energy. These are on a level playing field, and they are hybrids. Okay, does that make sense? Now, what kind of geometry? So if you further recall, we'll copy this. Copy. If you further recall, the s orbital was a little sphere-y thing there. That was our happy little s orbital, right in the middle. And we show all these things, but what's hard to really grasp is that they're not existing side by side. They're all existing on top of one another. So we had, the p on the x-axis and the p on the y-axis and the p on the z-axis, and they're all kind of smashed into the same space. It's like clouds of gas. They don't occupy the same space, but they're kind of superimposed on one another. Well, instead of now, so if we had that, well, the S is just straight around the nucleus. There's no orientation to it. When you're building something, there's really no way to put something in an s orbital. It's almost like their nuclei would collide. And you've got those p orbitals, so those are right straight along the x and the y and the z axis. So that would make things at 90-degree angles to one another, but that's not what methane's doing. These aren't 90-degree angles. What are they? Do you remember? These are 109, I think. 104.5. They're between 104 and 109. They're somewhere in there. They're more than 100 and less than 110. Well, when we get rid of the individual s and p's, we'll cross those out with great vehemence. These sp orbitals, these sp3 orbitals, look like this weird amalgam. So they don't look like an s, they don't look like a p anymore. They just look freaky. I will never ask you to draw them. That would be stupid. And what these all do is form the kind of geometry that, and I'm drawing this very badly, imagine that that's three-dimensional. The kind of geometry that you see with this thing, and I'll add a picture of it. It gives you the kind of geometry that you see with this, where they're heading in 4 different directions. So now we'll look at the slide and see if it makes a little bit more sense. Methane. The level 2 orbitals, the 2s and the 2p's, combine to form hybrid orbitals. There should be an s there, I think, called an sp3 orbital. So you take 1 s and 3 p's, you throw them in the pot, what you get out are 4 identical sp3 orbitals. So here's a question for you. If 1 s orbital plus 3 p orbitals equals an sp3, what do you suppose 1s plus 2p orbitals equals? sp2. Never forget how clever chemists are. sp2. If you take 1s and you add it to, 1p, you know what you get? An sp. Yes, ma'am. The only way this ever makes sense to me, and I still get baffled from time to time, is when I think about it in terms of actually drawing that, going back to that old orbital notation. I think it's because I'm a really visual learner. So then I can look at that and I can say, oh, okay, I take one s orbital, and then n, remember, can be any main energy level. This could be 3s and 3px, 3py, 3pz. It could be 2s, like we did with carbon. I throw those three things in the pot, and now I get 3 equal orbitals. sp3 and sp3. I'm just going to see if I can copy that. Yeah, I have always found this concept challenging.
But with the original orbital notation that we were working with, like the carbon, there was 1s and 2s. So with that, do you do 2s plus 3s, or plus 3p?
Hold on, I'm not understanding the question. Let me...
Two different s's. There's 1s and 2s.
But the only ones... Oh, that's a great question. So let's go back to that. Here with the carbon, yeah, it's got a 1s that's full up, but that's not valence. And that's important to remember. So this exists, but it's inner level. So here we're, because the valence electrons are really the only ones that are participating in the bonding. So you're just looking at what's, in essence, if you did noble gas notation, what's after the noble gas? Which orbitals are beyond the noble gas, because those are its valence. We only do this with the S and P block. Those are the ones that have the S and P orbitals. What happens in the D block is a whole nother animal, and it's way beyond what we're going to ever talk about here. You know that those things are delocalized. They're running around. They're sleeping in every dorm room on the floor because the floor is empty. It's just all kinds of chaos. This is a more controlled chaos. There are some rules to it. So why does carbon form 4 hybrid orbitals? And I just said that some things only form, so how many hybrid orbitals, so how many, okay, here's a good question. How many hybrid orbitals do you get when you get 3sp3? 4, yeah, because you get the same number of orbitals out that you put in. So how many orbitals do you form when you form an sp2? 3. Do you see why? 1 plus 2 equals 3. How many orbitals do you get when you form an sp hybrid? 2. Okay. So, where are you between what language are you speaking, who are you, this is, I'd rather have my fingernails pulled out, and, oh, okay, that's obvious. 5 is, oh, that's obvious, and 0 is just pull my fingernails out now.
On what part?
On the idea that this can happen, and on the idea that, you throw 1 S and 3 P's together, you get 4 sp3s. I think the math is pretty easy, right?
I'm a little unsure of why it happened.
Okay, that's fantastic. So let's talk about why it happens. And why, okay, so I get that methane would form, carbon can bond 4 times. Like I said, the first day of organic chemistry, if you take organic chemistry in college, the first day, if you have a good Dr. Peter Norris, okay, put up 4 fingers. That's how many times carbon bonds. 4. Can you count to 4? Good. Let's go. And then it was off to the races. 4. 4, 4, 4. How many times can carbon bond? 4. How many bonds does carbon make? 4. How many times does carbon bond? 4. How many things can carbon bond to? 4. You get the picture. So I get, because carbon has 4 valence electrons, it's going to bond covalently almost all the time. It's very seldom going to, it does form ions, but it's right there in the middle. Things that have 4 valence electrons tend to bond covalently because it's a big hassle to get rid of 4, and it's a big hassle to gain 4. It takes energy to do that. So let's talk about things that form some of these other hybrids. Let's actually check the slide to see if there's anything else we should include from that. Well, here's a nice picture. So, and this is kind of what I tried to draw in my very bad way. There's an S, there are the P orbitals, and what we get out of it is this sp orbital, sp hybrid. And my sense, and I am not enough of a atomic physicist, because I'm not an atomic physicist at all. For Pete's sakes, I'm a biologist. My sense, though, is that the shape of a sp3 and an sp2 and an sp orbital those hybrid orbitals are all pretty much the same. They look like this weird stunted drumstick of some sort, or like a dumbbell that one half got shriveled up. I don't know what they look like, but my sense is that they're just kind of different sizes of that. Okay, so hybridization makes these things possible, and that's all well and good to say. Let's look at why these things do this, and sort of how it happens. So nope, they're already gone. From your molecular geometry lab, let's look at something that was linear. What, beryllium chloride? Yes? Nope, that's a terrible example. Oh, no, that's not a terrible example. Let's do beryllium chloride, or beryllium dichloride. So we've got BeCl2. And in that Be, I'll be darned if I can find a single periodic table in this room. What is its, how many valence electrons does it have to start with? How many valence electrons does beryllium have? 2. So beryllium is 1s2, 2s2, and these are not valence, so they're not participating in bonding. Now, if you just look at that right off the top, doesn't it look like beryllium should be happy? I mean, it's not as happy as it could be if it was a noble gas, but I mean, S2 is a full orbital. It's better than nothing. It's better than a half orbital. So if we look at beryllium, we've got 2s, and then we have those empty orbitals. I'm having a double of a time rating today. 2px, 2py, 2pz. There's nothing in those. They're just empty. So if beryllium splits up these electrons and hybridizes, let me change colors on this, these two, and so now we have a 2sp, 2sp. It's still got the 2px. Let me shift that. I guess that would be 2py, 2pz. Only one of its 2p orbitals participated in hybridization. But it's now got how many places to form bonds? 2. These two hybrids each have 1 electron in them. You tend to form bonds where you've got 1 electron in an orbital. And so now beryllium is going to stick, I'm going to draw the little weird thing, one of those out to one side, one of those out to the other. There's my beryllium. It's now got 2 orbitals that can form bonds. So it forms a linear. Okay. Yes, ma'am.
What would the math equation be?
What would the what?
The math equation,
For the hybridization? Here, let me copy this over to a clean slide. So here you have an s orbital plus a p orbital equals an sp orbital. So you had one s and you had one p. I should say you have one s orbital. It's not the one s orbital. It's actually the 2s orbital in this case. Do you understand? Is that clear? Okay. So you get two sp orbitals. And they're equal. Is it making more sense or less sense?
That's just where I get confused because there's two CLs.
Okay, so let's look at how the Cl does this. The Cl doesn't actually have to hybridize. The Cl isn't hybridizing. So you've got the beryllium. We'll put the beryllium right here in the middle. And it now, and I'm going to draw this badly, of course. This has an sp with one electron in it. I'll draw this in a different color. I'll see if that makes it any better or worse. And here I have an sp with one electron in it. I'm probably going to have to shrink this. So now our chlorine comes along. Chlorine has one s, whoops, not one s, what's chlorine on the third? 3s, 3px, 3py, 3pz, 1, 2, 3, 4, 5, and it's missing. So basically that 3pz orbital is what's going to participate in bonding with chlorine. Chlorine's still going to have all these unshared pairs around it, and this orbital is going to participate in bonding with that. So chlorine does not have to hybridize. Not everything hybridizes. There are things that don't hybridize. Not everything is hybridized all the time. Basically, well, let's not get into when it happens. So what do I want you to know about hybridization? I want you to know that it occurs. I want you to have the association of which types of hybridization give you what shapes. So sp hybridization gives you what shape? It's linear, it's a straight line. Because you've got those two orbitals basically hanging off to either side of whatever it is that's hybridized. So let's look at something that gives us trigonal planar. Is it boron trifluoride, I think? Yeah. So BF3. And this is another case. The halogen here is not going to hybridize. It doesn't need to. The halogen's got one place to bond, and it'll do that. So let's look at boron. How many valence electrons does it have? Yes, 3. So it's in the second period. So it's 2s, 2px, 2py, 2pz. So it looks like that, right? So just looking at that, can you tell how many orbitals are going to get mushed together? How many electrons do you have? 3. And therefore, you're going to mush together 3 orbitals, so each of them... Basically, this is so everybody gets their own room. You know, this is like you go into the dorm, and there are 2 people in this room, and there are a few steps between this room. So you and your friends take a bunch of sledgehammers, and you remodel the entire dorm floor so that everybody has their own room, and nobody has to climb any more steps. The best analogy I can come up with at the moment. These 3 are going to get mushed together, and boron's going to come out with a 2 sp2, 2, whoops, sp2, 2 sp2, and then it'll still have its little 2pz that nobody invited to play and doesn't have any electrons anyway. And each of these has 1 electron, yes?
Why doesn't the 2pz get included?
Because there aren't enough electrons to go around. If boron had 4 valence electrons, 4 orbitals would go into the hybridization.
Is that using one of the 2s electrons
Yes.
to include?
Yes, so one of these electrons hops over to here.
Okay.
So always include an empty one for the second electronegative.
Well, basically, however many electrons you have, you're spreading them out over a whole series of hybrids. So, yeah. And I'm not going to ask you to predict what kind of hybridization will occur. I think that's beyond the scope of the class. I want you to be aware that it happens. I want you to get the geometry piece. That's really what I want you to get. So let's look at what kind of geometry this would make. Let me shrink all of this. Thank you. So now we have boron sitting there in the middle, and I will do these in all different colors just to make it really exciting, if that's the word we want to use. So we have boron with that, and boron with that. I'm drawing this very badly. And boron with that. That's as far away from one another as those electron clouds can get, right? I can move that up a little bit if it's hard to see. You know, and this has one electron. Well, let me just do the electrons in black. This has one electron, this has one electron, that has one electron. It's got 3 hybrid orbitals that can bond. So what shape is that going to take? Let me see if I can turn this. Why, looky there, it appears to be a triangle. That'll give you a trigonal planar. Because you've got 3 things, they want to be as far apart from one another as possible. That's flat, like they're pressed between 2 panes of glass, out to the corners of a triangle. Okay, so hence, linear molecules are the result of an sp hybridization. Trigonal planar molecules are the result of an sp2 hybridization. And oh, these tetrahedral, my caltrops and calfarts. Talked about what caltrops are, right? Medieval siege weapons used against cavalry. 4 spikes, you throw them on the ground. Any way you throw them, a spike lands up. The opposing army's horses march over them. Their horses are all lamed. Poor horses, they didn't ask for this. Also used as an anti-vehicular weapon in a lot of James Bond type movies where, you know, a hatch in the back of his car opens and a bunch of caltrops go spinning out onto the road and all the cars behind him suddenly have flat tires. So how do you get a caltrops? How many orbitals have to be participating here? 1, 2, 3, 4. So what kind of hybridization would that be? To get, and we call that tetrahedral. 1s plus 3p, which gives you sp3. That gives you tetrahedral. Now, if you go into a chemistry class anyplace else and say, oh yeah, sp3 gives you a caltrops, they will not know what you're talking about. Please don't do it, or don't tell them you had me for chemistry. But this is what I kind of want you to know. And it doesn't hurt to know, like, if you add, I mean, I think I've asked this question on tests before, and this is what I consider like a Grant's tomb question. Who's buried in Grant's tomb? Grant. Yes. A hybrid orbital made up of 1s and 3p is called what? sp3. Like, I've asked that question. People have missed it too, but that's okay. You know, so I think it's totally fair game to, you know, to say 1s orbital plus 1p orbital gives you what kind of hybrid orbital? sp. So it's not horrible, but I think it's confusing to approach. Okay. Let's finish these up with a few little sort of fun facts, and then I'll just give you time to work. So, Intermolecular forces, those of you who play any kind of sport are probably better at this than I am. I always struggle with inter versus intra. Intramolecular forces are forces inside the molecule. That's what we get from the covalent bonds. The way that you know how I remember this? Interstate.
Yes, I was just thinking that.
Yes, interstates go between, like interstate commerce, because you do all the social studies stuff, and intrastate commerce. But I think of like interstate highways go from one state to another state. You use whatever mnemonics you can. So intermolecular forces are the forces of attraction between two molecules. And basically, the stronger those are, the higher the boiling point. So for something like ethanol, and I've got isopropyl alcohol. It's mostly gone. This isopropyl alcohol, Gesundheit, pretty volatile. My isopropyl alcohol has been replaced with water. I wonder who did that. Anyway, so isopropyl alcohol, if you've ever had a swab for a blood draw or something, it evaporates pretty quickly, so it leaves your skin kind of cold. It's got pretty weak forces of attraction between the molecules, so it boils at a much lower point than water. We think of boiling as like bubbles. Boiling is just the point, it's the vaporization point. It's the point where it goes from being a liquid to being a vapor. So generally, intermolecular forces are weaker than the forces inside the molecule, and they're much weaker than the forces between ions and an ionic compound. How did you prove that in here? You proved that. Huh? What'd you do with them? You melted them. You stuck a candle under them. Pasha. You stuck a candle under them, and the ones that had the weakest forces holding the molecules together melted. Like the phenyl salicylate melts almost instantaneously. Phew, it's gone. The salt, the sodium chloride, has got incredibly strong bonds between all those ions. It takes a lot of energy to melt it, hence why you can make, we've talked about this, a gift for somebody you love of a salt cushion that they can put on their face when they're all stressed out. And intermolecular forces are also typically weaker than the forces between like atoms in a metal. You know that copper melts at a higher temperature than wax or sugar or something like that. So the lower the melting point, the lower the boiling point, the weaker the forces. That's almost Grant's tomb. That's pretty self-explanatory, I think. Okay. Molecular polarity. Where have you heard the term polar before in this chapter, in the last chapter? Polar covalent bonds. So what did we say a polar covalent substance had? It's got an electron hog is what it's got. So a polar molecule tends to have, and I'm, for lack of thinking of a better example, so if this is two atoms that are bonded together molecularly, and that big mushroomy thing around it is the electron cloud, which one of those is more electronegative? Who is hogging the electrons? A is hogging the electrons. A must be more electronegative. So if A is more electronegative, it's got a whole bunch more electrons around it. Overall, there's a region of partial charge. Okay, so A is more electronegative. A has got more of the electron cloud around it. So if there was a region of partial charge on this molecule, where's the negative part? A or B? Where's the negative part? If I tell you that part of this molecule has a charge, which part is going to be more negative? because electrons are negative. It's got this big bubble of electron hanging out around it. It's like one of those stunt people who does like a head full of bees, like the bee beard, you know. Yeah. A's got like this swarm of hornets, electrons, around it. So they designate it as something like this. I don't even know what that means, but I'm trying new things. I usually just say, yeah, this part's pretty negative. I'll forget about it. That's negative, and that's positive. So what that forms is poles. Just like a magnet, where you've got a north and a south pole, this forms a positive and a negative pole on this molecule. So we call it a dipole. What that means is that if you have a whole bunch of these all swimming around in the same vessel, they're going to line up in a particular way because the little positive ends are attracted to the little negative ends, and the little negative ends are attracted to the little positive ends. I'm doing a fairly bad job of this, but you get these moments of attraction. They're all moving around, you know, because all molecules are in constant motion. But as this one, for instance, moves, as it gets close to the end of this, there's this moment of like really strong attractive force. You know, and then it might move on past, and then this one might move, darn it. This one might move on this way, and it gets there for a second, and there's this moment of strong attraction. These don't tend to extend through a whole substance. So they tend to be kind of brief as things move past one another. They'll line up for a moment, and then they keep moving. So it's like flirting with people at a party rather than a committed relationship. While they're flirting, the attraction is very, very strong, but it doesn't last. You know, it's this instantaneous boom, and then it's over. Okay. And that, I think, makes more sense of the slide, that we have these equal but opposite charges, and they're close. So it's only when they're right next to one another, it's not all the time, and it's sort of transient. Oops. As much as things in a molecular substance touch, they're not holding hands. You know, they're not overlapping orbitals or anything, because these are molecules, they're independent molecules. So Gesundheit, they may bump up against one another, but they're not physically connected, no. So hydrogen bonding is a little bit more intense. Remember our friend Mickey? So we've got our water with those two unshared pairs. So water's got a couple things going on here. It's got a strong dipole. But more importantly, it has these unshared pairs down here. So when you have, those unshared pairs are very attractive to the hydrogens. So water actually lines up with all of those little unshared pairs and all those little hydrogens. And this is not so transient. They actually line up this way in a glass of water. And I can copy this whole mess and take it to a cleaner slide, if you would like. Oops. So it starts to look almost like geometric tiling. It starts to really look almost like the way ionic substances form those lattices. It's not that intense. It's weaker than that. But they sort of line up and hold hands because there's a really strong force of attraction between that hydrogen and those unshared pairs. Again, they're not touching, they're not holding hands, but they're lined up in this sort of formation. This is actually why we have surface tension on water. So a lot of the characteristics of water, hydrogen bonding happens in other substances, but water is the one where it's kind of out of control. And a lot of the characteristics that we take for granted with water are due to hydrogen bonding. So the fact that it's got surface tension, that meniscus that you're so used to reading is a result of hydrogen bonding because the water pulls up the side of the glass and drags its buddies with it. It's cohesive and adhesive. That's about all we can say about hydrogen bonding. And this is the last thing. I don't expect you to know a whole lot about this. I want you to know they exist. London dispersion forces. They're very weak. They happen between nonpolar molecules and noble gases, which aren't supposed to have any forces of attraction to anybody. They're totally above it all, every now and then. Because those electrons are in constant motion, if we have atom A and molecule A and molecule B, and this thing's got its whole electron cloud around it, and this thing's got its whole electron cloud around it. I guess I should make these two molecules of the same thing. At any given moment, because remember, we can't really predict where electrons are. They're moving randomly at all times. Maybe a bunch of electrons end up over here and a bunch of electrons end up over here. And for 1/1000th of a second, there's a dipole. And they're attracted to one another. And then it's over. So this doesn't even rise to the level of flirting. This is like you catch somebody's eye at a party and you have like a split second of, and then you're like, oh, where are the chips? And it's all over. So they do happen. They're short-lived, but you should be aware of them. That's it, folks. So what I'm going to do is give you time to work. Do you have questions? Do you have questions on the homework? Questions you've been storing up? You want to see BrO31-, the bromate ion? Okay. So we've got the bromate ion. This is Gooch conforming. It should work for Gooch math. So bromine comes in with 7. Oxygen comes in with 6 times 3. We have 7. We have 18. 25. And because it has a -1 charge, we add 1, so it has 26 valence. There are 4 molecules, and everything wants 8. That's 32 octet. Minus 26. 8 shared. So divided by 2 equals... Oh, well then yeah, you're right. I'm sorry. I can't do arithmetic. Does that make it better? You were right in the first place and you shouldn't have listened to my crazy answer? Okay, never mind. So, 3 bonds. Hey, that works. And then this would have an unshared pair, right? And then...
Oh yeah, 42.
I like how you stepped back from that. That was nice. Okay, so, and then of course, is that what you have? Okay.
Did you do the B?
If I can find it, yes. Okay, so we've got 24 valence on, this is 43, or 42B. For octet, we've got H only wants 2, carbon wants 8, oxygen wants 8, so 6, 16, 16, 32, 38. So 38 minus 24, we have 14, so we have 7 bonds. Okay. We know carbon's going to be in the middle, and we'll start by just hooking carbon to carbon. We know hydrogen can only bond once, and this carbon needs to bond to 3 more things. 1, 2, 3. So that gives us 4 bonds. Carbon, oh, I bet I know the trick here. Well, hold on. So if carbon is bonded to, and it's got to be bonded to one of those twice, which gives us 2, 3, 4, 5, 6, 7 bonds. Okay. And then that whole thing, and then of course your unshared pairs, so. And this would require resonance. And are all the carbons happy? All the carbons are happy. We like to keep carbon happy. So yeah. I'm trying to think if there are other possible structures for that. Can't think of one off the top of my head. Well, no, sure. There could be another structure for that, couldn't there? If that was a OH and a double bond. If that was a hydroxyl group.
How many unshared?
So let's see. Had 24 valence and it's sharing 14, so it would have 10 unshareds, 2, 4, 6, 8, 10. And there would be resonance with that because the double bond could exist in more than one place. Now wait, you know what? There's another possibility for the structure of this one. And then when all else fails, I'll look at what your book says. So could it look like this? One, 2, 3, 4, 5, 6. No, so it would still have to be double bonded to one of the oxygen. Or, wait, that's happy, that's happy. I think my first shot was the best. Yeah, I think my first shot was definitely the best. Scrap that. Can you do what? No, you should not go randomly mixing oxygens and hydrogens.
Or did we just say requires resonance? That second one.
Of course you do.
Okay.
How would the resonance look?
the
Let's see. So this side of the structure wouldn't be changed. I mean, that's your resonance right there. Other questions on the homework? Because there are only 2 orbitals that can form a bond here. So if something formed a double bond, what would that look like? I'm trying to think of something that, well, actually doesn't. Does O2 form a double bond? Okay, let's look at O2. So oxygen is second main energy level 6. So 1s, 2s, 2px, 2py, 2pz, zoop, 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 zoop. 1, 2, 3, 4, 5, 6. Well, lo and behold, oxygen has, these 2 can share, whoops, And those two can share. Forms a double bond. Overlaps two orbitals. Does that make sense?